When you encode text into binary, it's often nice to use as little data as possible, so you might naturally wonder, is there some kind of fundamental limit on how efficiently text can be compressed? The default encoding with ASCII is pretty inefficient. Each character is represented with 8 full bits. If you apply a little cleverness associating more common characters with smaller bit strings, you can get this down to an average of around 4 bits per character. And then much smarter methods than that leverage patterns among long sequences of text can get even better still. But again, what's the limit? I'm guessing many of you might have heard an estimate here. I will share one at the end. But much more interesting than any single numerical answer is how you would even approach answering it. This question dates back at least to the 1940s, with Claude Shannon's seminal work that kicked off information theory. Now what's very interesting is how the math that he developed to answer questions like this has turned out to be surprisingly useful for modern machine learning. To take the salient example of today, when large language models are trained, the pre-training portion of that is usually described as being about next token prediction, specifically using something called cross-entropy loss. Now that term, cross-entropy, has its roots in information theory. But what's also interesting is that one of the conclusions of information theory says that prediction and compression are mathematically equivalent. They turn out to be two sides of the same coin, which means you can entirely reframe how you think about the pre-training objective as not really being about next token prediction per se, but instead as being about creating the most efficient possible text compressor. Later I'll explain exactly how that works, but when you do, I think it offers more clarity on what this notion of cross-entropy really is and why you're using it. Also, I don't know about you, but to me at least, there's just something very intriguing about using compression as a fundamental objective while pursuing intelligence. In fact, some people have gone so far as to say compression is intelligence. Now, as stated, that's a hard claim to judge rigorously, since intelligence is such a squishy and ill-defined term. The safer claim would be that the mathematical theory of compression is bizarrely relevant to artificial intelligence. Still, the pithy phrase is thought-provoking, so this is the first in a trilogy of videos aimed at laying down the mathematical fundamentals to assess what this claim is really getting at. For the next 30 minutes or so, you and I will be focused on understanding the limits of compression, and seeing if we can get you to feel like you could have rediscovered the core idea behind Shannon's noiseless coding theorem. Doing so involves rediscovering a few key definitions, namely those of information and entropy. And it might sound a little weird for me to describe definitions as something to be discovered, but great definitions are often the residue of some kind of insight. See, these two specific terms are really not hard to define in the sense of laying down a formula for you, but doing so too early would spoil a good story. It is much more fun to see how you are inexorably drawn to them by asking about the limits of compressing language. And what I want you to notice by the end here is how we can't really answer this question, or at least Shannon couldn't, without necessarily engaging with some notion of intelligence. We will get to modeling language, which is wonderfully complicated, but it helps to warm up with a simpler example containing the same essential ideas needed for our path of rediscovery. Imagine you have a robot that we have sent to a faraway moon whose job is to wander the surface and collect data. From here on Earth, we send it instructions for how to move that are going to be limited to 4 very simple possibilities. Move up, down, left, or right, each one with a fixed step size. The nuance will be that these instructions are not uniformly distributed. Half of everything we send is up, 1/4 of the instructions are down, 1/8 are left, and the other 1/8 are right. It's a little contrived, it's meant to be a simple example, and in that spirit of simplicity, we're also going to assume that every instruction is independent. They are sampled from this distribution regardless of the preceding context. When we send data to this bot far away, we're doing it as a stream of bits, 1s and 0s, and it's very slow and costly to do that, so the natural question, the warm-up puzzle for you today, is to ask what is the most efficient possible way to encode these instructions as a stream of bits? And here, we might imagine 3 students who each attempt an answer. One who's straightforward, one who is clever, and one who is very theoretical. The straightforward student immediately raises their hand and says, well, for each of these 4 instructions, we could just use 2 bits. Maybe 00 encodes up, 01 encodes down, 10 encodes left, and 11 encodes right. On the receiving end, this makes it very easy for the robot to decode. It simply breaks up the bit stream into chunks of 2, and translates each chunk into the appropriate instruction. Now the clever student points out, well, that does nothing to take advantage of the fact that up comes up way more frequently than left or right. They propose a method where we use a different number of bits for each instruction. I'll explain it in just a second, but I do want to call out the fact that as soon as you let different instructions get different numbers of bits, it's certainly not obvious that the robot is going to know how to decode it. After all, it needs to somehow know where to draw the dividing lines. Now, being very clever, the second student has thought that through, but it's easiest to explain if I just kind of lay it all out. What they suggest is letting the single bit 0 represent up, letting the two bits 1, 0 represent down, using 1, 1, 0 for left and 1, 1, 1 for right. You can calculate the average number of bits per instruction that this would require with a simple weighted sum. Half the time, only one bit is used, a quarter of the time, 2 bits are needed, and the remaining times, you need 3 bits. When you add this all up as a weighted sum, you get 1.75 bits per instruction, which is indeed better than the more naive approach of a flat 2 bits per instruction. The second student is spending more bits on those last 2 instructions, but because they come up so much less frequently, this is more than made up for by using only 1 bit for that most common instruction. And you can see this efficiency bear out empirically too. This right here is a set of instructions sampled from that distribution. You'll notice lots of ups, about half as many downs, and even fewer lefts and rights. When you turn each symbol into the appropriate bit string following this encoding, the resulting sequence of bits is indeed shorter than what the naive method gave. But I hear some of you asking, how does the robot know how to decode this? Can we be sure that there's an unambiguous way to draw the dividing lines? In the lingo of encodings, each of these 4 bit strings used to encode the instructions is called a code word. And as we step through things here, see if you can figure out what rule the clever student was following to make sure that their code words don't conflict with each other. And really, you just need to look at an example bit stream from the robot's perspective and think it through. Let's say that that very first bit that it receives is a 1. So far, this could be encoding any of the last 3 instructions, down, left, or right. If what follows is a 0, then it can only be down. There is no other possibility. So the robot can register that as a complete instruction. From there, starting fresh, if what follows is a 0, that must be encoding up, since there is no other possibility. Nothing else starts with a 0. After that, if they see a 1, this is so far ambiguous, it's the prefix for any of the last 3 code words. If the next bit is another 1, it remains ambiguous, it's the prefix of the last 2, but that following 0 then makes clear these 3 bits must have been encoding left. In short, all the robot has to do is read in the next sequence of bits until the moment that it forms a complete code word, at which point it can register it as a complete instruction. If you step back and think about it, the key constraint for this all to work is that no code word can be a prefix of another one. For example, let's say you tried to introduce some 5th instruction that had the code word 100. That would cause conflicts, because after reading 10, it's not clear whether that's supposed to be down or if it's supposed to be the start of this new 5th instruction. When you avoid this kind of conflict, an encoding method like this has a special name. It's known in the business as a prefix-free code, or what is confusingly synonymous, it's actually more commonly known as a prefix code. And there's a really nice way to visualize choosing prefix-free codes with a certain diagram that represents every possible binary string. This diagram also has some helpful parallels with how I want to show entropy in just a few minutes. It's probably decently intuitive what's going on if you just pause and stare at it for a bit, but I'll call out the important features. Each layer shows every bit string of a given length, and you'll notice everything that starts with a 0 lives on the left half of this diagram, and everything that starts with a 1 lives on the right half of the diagram. And that same idea continues recursively as you go up. So everything starting with 0, 0 is above this quarter of the diagram, everything starting with 0, 1 is above this quarter of the diagram, and so on. In particular, the key property is that every binary string in this diagram is a prefix for everything that sits above it. So when our clever student chose to allocate a single bit 0 to represent the instruction up, they were effectively consuming half of the space of all possible code words by doing so, since everything starting with a 0 is now prohibited based on this prefix-free property. Similarly, allocating 1 0 to down eats up another 1/4 of this space, and the remaining 2 instructions each eat up 1/8 of the space, You can just